Okay, so welcome back to the full methods lecture. Last time, what we did is we looked at this swap function because we wanted to do some program verification. Let's check. Okay, because we wanted to do some program verification and check whether it works the way we are expecting to. And we said the way we can check this is with contracts, and we can check whether these contracts are kept by the function. So here, a contract can consist of a precondition and a postcondition. And the postcondition here actually is the important one. Here we don't need any precondition, or we don't have any precondition right now. But the postcondition basically says the x that we have after the execution of the method needs to equal to the y we had when the execution started. So basically this x out equals y in, so the x after the execution is this y. And then also the y after the execution is this x that we got inside, and that's actually the swap. So we're going to swap the values of this method. And then we looked at a first attempt to do this. And I think our first attempt looked like this. So we gave some swap example. We said x might equal 1, y might equal 3. And then we would expect that in the end, well, we didn't even encode the condition here. We just tried to encode the swap itself directly by following the lines of the program. And then we saw that this actually is unsatisfiable. And the reason that it was unsatisfiable was that basically here we are stating equality of these values. So x equals x plus y. That's what we're basically saying here. In the program, this would have been an assignment and would have been fine to assign a new value to x. But here, this basically only works if y is 0, right? Because then x would be equal x plus y. And then this one here, where well, y equals x minus y, that's probably also fine with, well, it's only fine with 0 for y if x is also 0, right? So basically, there would have been a solution, and the solution would have been zeros, but that's not what we're looking for. We're looking for all possible inputs, right? And we gave an example input here. So yeah, this means that this doesn't work, and we already saw a potential solution of how to make it work. And we said the way to make it work is to use this single static assignment. Whenever we assign a variable, we don't reuse that variable. We are creating a new fresh variable only for this purpose. And then, of course, this assignment should work. So if we do that in the piece of code that we had right there, then we would actually say, well, this x that we assign here, because that's in the program, this x was an assignment. So we could say, well, let's call this x1, right? And then here we have a new assignment, so let's call this y1, and or let's even call it y2 because it was in line 2, doesn't really matter. And then here, this x, we could call it x3 because it was in line 3. So now we have basically introduced fresh variables, but of course, we have to declare them as constants as well. So, well, the names don't really matter. So let's say we now also have the fresh variables here, and there would be x1, y2, and then we said also we can use an x3 because that's the last assignment that we do. Is this better? Let's see. Let's see first whether it's even satisfiable. Yeah, now it is satisfiable. But we see some strange, well, maybe not so strange. Is it fine? I don't know. So now that we have made something satisfiable, let's try to encode the post condition and see whether it's really fine. So, or did anybody see any issues and wants to change something? So that's again the piece of code. The post condition here says the x that we get out equals the y that we got in, and the y that we got out equals the x that we got in. So we can just write this as an assertion. Let's just write exactly this, right? We have an end between two conditions, two equalities. So the x that we get out, which x is that? That's the last one we assign, right? That's x3. So x3 is actually the x that we get out, and we say this needs to equal the value of y that we got in. So y that we got in is this 3. Yeah, that makes sense. And then here we also want an equality that the y that we get out, so what's the last assignment to y? That's y2. We want this to equal the x that we got in, right? Okay. So let me just check. Yeah, it's recording the sound. Good. Now this would be the post condition, right? And if we run this right now, we get unset. This means that this particular case that we were trying doesn't satisfy the post condition. That's not good, right? There's something wrong because, well, either. So what does it mean? Let's go back to the slide. If this post condition is not satisfied, this means the contract is violated and the swap function doesn't work, right? Because it's supposed to work. The contract says this swap function really changes the values of x and y in the output. So either this method is incorrect or our encoding is not quite right. So who thinks that this method is incorrect? Who thinks that our encoding is not quite right? Should be everybody else, because there can be only these two things. So what did we do in our encoding? Let me try to put this side by side. So, yeah, we can, no, that was a bit too much. So we can see those assignments here, right? So let's go over them line by line, whether we really, whether we really captured all of them. So that's somewhat, yeah, aligned now. We said for every assignment, we create a new fresh variable. That's this single static assignment. So we only do single assignments. So here, this x equals x plus y. This means we create the x1, which equals x plus y. This looks fine, right? Next line. Y, we say, well, it's a new one. That's the variable y we created in line 2. So let's call it y2 equals x minus y. Yes, exactly. It should take the value that we already updated. Here, x now no longer is the input x, right? This x that occurs here actually now has the value of the input x plus y. So we need to use this new variable that we defined, the x1, instead of the regular x. So here we should actually use the x1, right? Did we change y so far? This, can you see this? You probably can see this y, right? Yeah. So this y, did we change this y so far, or is it still the right value? Still the right value. We didn't do any assignment to y. Great. Now the x3, the last line, which x should we use again? So this x is not really the x, right? Yeah, must be the x1. And now this y is not the original y, it's the y2, right? The one that we just assigned in the line above. Okay. Now let's give it another try, right? Or is there anything else? Let's give it a try. Okay. So now what happened is we get a model. Let's look at this model. We know something about the input, right? We said the input x was 1 and y was 3. Yes, this was our input that we defined with these assertions here. So of course that should be preserved. Great, it is preserved. Now, what are these outputs, right? The outputs are the x3. x3 should be the value of the input y. That's 3. Great. And y2 is the output, which should be the value of the x input. Great. So yeah, for this particular example, the swap works. Now, how do we check it? Not only for this particular example, but for some other ones. We can, of course, now change here the values. I don't know, what's a tricky thing to swap? 3 and 3. Let's try if that works. Yeah, 3 and 3 also swaps. Great. Can we swap negative numbers? Which one was the output? The output is the y2. So yeah, y2 is now the negative number, and the x3 is now the value of y. Great. So yeah, are we testing? We want to do verification, right? We don't want to test every single case. We should ask the SMT solver to do this, right? So maybe we shouldn't fix those cases, right? So let's just comment this one out. We don't really, or let's just delete it. We don't really just want to swap those things, right? Now, we run this. Strange model, zeros. Well, if we swap 0 with 0, yeah, that's also fine. Same result. So how do we check that it works for all values? What do we want to check? Do we want to check satisfiability? What we are now checking is satisfiability, right? And we might want to check validity. Yes. How do we use a satisfiability checker to check validity? Yeah. Check if it's not if it's the negation is the negation of. Yeah. So if we negate this contract, then find an assignment that satisfies this, it means we have found an assignment that violates the contract. And if we have found something that violates the contract, we know the contract doesn't hold, right? So we're going to try to find something that violates the contract. So we need to negate the contract and then see if we find something that satisfies this. And we don't. So this means that there is no way, so now x and y are completely free to be set whatever we want, right? So there's now no way to violate the contract. This means the contract holds. So this swap function really works for all integers. Great, very good. So now we have verified this. Here it says, well, encode the negation of the post condition. Exactly, that's what we have to do. Great, so we have now verified this these 3 lines of code. Good. Yeah, this was the single static assignment. We can use some other identifiers or variables here. Well, the numbers are slightly different, but it's basically the same, right? So we first converted the code into single static assignment, and then we express it in SMT. Yeah. Now, the question is this single static assignment really what we are, well, hoping it to be? So in theory, we just applied this single static assignment, right? We said, well, this kind of, somebody told us to apply this, so let's apply this. We should, of course, check whether this really works. So the way that we could try this is we could try to find some example that violates the single static assignment. But now that's not so easy to encode in an SMT solver, right? Because what would we have to do to verify that a method like single static assignment works in an SMT solver? How could we verify this? We have a particular program, right? We encoded this with single static assignment in SMT, and we could check that this program satisfies the contract, right? Of course, you could define some contract for single static assignment, but what would this require for you to encode in SMT? We want to kind of make sure that single static assignment always works, right? So even if we would somehow encode this, we can't encode this, right? Because this is an assignment. So we didn't, our way to encode this program was with single static assignment. So we would need an alternative to single static assignment, encode that in SMT, and then check whether the program with single static assignment agrees with it on all cases. that's really, maybe difficult because we need to come up with an alternative to single static assignment. And in addition, we would then have only proved it for this one program, right? To prove that single static assignment works in general for all programs, we would need a way to model all programs in SMT, which is much more complicated. So you can probably do that with a theory of data types, and then you can try to express something like single static assignment. Very likely it doesn't work because of undecidability issues. So we know that in general we can't even determine termination of a program if the programming language is powerful enough, expressive enough. So we also cannot determine equality, because if we could determine equality of the output of two programs and we have one program that surely terminates, we could check kind of termination in some, well, maybe clever way. Okay, so something like this, you probably wouldn't do this with an SMT solver. You would probably write a proof by hand because you need to reason over all programs, and that gets a bit more tricky. So you would probably want somebody to prove this single static assignment correct. And yeah, turns out people have done this, and it basically is correct. I mean, we can intuitively see that the single static assignment does exactly the same operations on the variables as the original code, right? We didn't change any of the operations. Now, the only question is, are we correct in terms of the assignments that they do to the variables, right? So, and if we imagine which variables are read and what are their values, and which variables are written and what are their values, then we can kind of convince ourselves that the variables, they simply have different names. So if we just always refer to the correct name, then the single static assignment must be correct. But of course, this would require a more rigorous proof. Also, the treatment that we did of single static assignment. So this single static assignment is a big thing, even beyond SMT solvers. We used it for SMT solving, but actually it's used in all kinds of compilers and optimizations. So the treatment that we had of the single static assignment was very simplified. We said every assignment, we basically introduce a new variable, and then every time we access some variable, we just look in the control flow, what was the previous assignment to that variables. And actually, our code usually just had very, very simple structure. We just had a linear sequence of lines, which is not the case for most programs. So very much simplified, introduce fresh variable, and then we said, well, if we want to have branching with an if then else or in a loop, we need to include all the possible predecessors from the previous code and just check what condition was there. So what is the current value of this variable? But actually, there are some optimizations because, well, if you analyze large pieces of code, you want to optimize it. There are optimizations, for example, for the minimal number of new names and also for optimized conditions of the branching. So yeah, minimal number of new variables. Maybe not every assignment needs a new variable. Maybe you can also reuse variables once you know that nobody will ever read them again, right? And then what does it mean, optimized conditions for branching? So what we would do is if we have kind of nested ifs, or even if we already left some condition, we will just have to collect all the ways how could we get there in any program flow, right? And this would pile up in our conditions to know which value does the variable actually have if there would be multiple program flows to get there. And you can imagine that some of those, they might be false because there are some program flows that simply cannot exist. But if you naively collect all of them, you will have very long conditions that you need to check to see what is the current value of this variable, because it depends on how many ways do you have to actually get to this point in the program. So there are lots of optimizations for these conditions as well. And then, yeah, many analysis tools and compilers, they use this single static assignment. So if you have any IDE and it checks your code, whether you have null pointer dereferences or whether you have, well, I'm not actually sure whether usage of variables. Yeah, but basically, probably null pointer dereferencing will check this. What is the current value of these variables at this program point? Could it ever be null? Or other checks that your IDE does in the background and then warn you that you potentially access some maybe uninitialized variable, stuff like that. This is all using single static assignment. And now let's look at a little bit more complex one. So if we want to basically have a maximum or a set maximum function that checks which one is of the two parameters is the maximum, and then if the second one is larger than the first one, it swaps them, right? So that then always the first one, the x is greater than the y. So now what is the challenge here? The challenge is that we have this swap in here, which is another method, but we already proved this method before, right? So how do we now? Oh, and we have this condition, which is even more tricky, right? Because we have to encode what happens in those cases actually. So here are the two methods, right? The one that we have here, and then the swap there. So now how would we encode something like this? We have again our input variables, then we have, well, some variables for assignments. We need to encode our precondition. Now the contract actually has a precondition. Why do we now need a precondition? In swap, we didn't need a precondition, right? But what is our postcondition of this set max?
Because we have to change the variable, so we need a two variable.
Yeah.
Well, if x is equal y, then x can't be greater than y.
Yeah. So our postcondition is actually that x is greater than y, so it's really the maximum. But of course, if you would have two values which are the same, there's no way to ensure this, right? So we would have an impossible case for our postcondition. And to basically say, well, in those cases, this method doesn't guarantee anything. We have this precondition. We could actually also make this a bit more robust. So how could we get rid of the precondition? So we need the postcondition because that's our contract and we want to say something about what this program does, right? So how can we get rid of the precondition? Can we move it to the postcondition? So the meaning of the precondition and postcondition is if the precondition is satisfied, then the program will guarantee the postcondition. And otherwise, we don't care. So this, if something is true, then something else must be true. This is simply an implication, right? So we could also move the precondition to the postcondition as an implication. We could say x in doesn't equal y in implies x out greater than y out. So this would be the same meaning, right? Then we would again have said if the precondition is satisfied. So if this thing on the top was if they are not the same value, then x will be greater than y in the end. And if they happen to be the same value, then the left side of the implication is false, which means we don't care what the right side is. So they could still be, one could be greater than the other, but we don't really care. Well, and we know they can't, right? But in theory, we just don't care. So an implication would be the same thing here. The question is, why would we not do this for maybe practical purposes? Why would you want to have a separate precondition labeled on your code? If you would, let's say, use these methods, and you see, well, nice, this method doesn't have any precondition, so I can just call it with whatever I want. But then the post condition actually says, yeah, but I'm going to check anyways whether I really want to do this. So it's usually for, let's say, practical purposes, it's much better to separate them, to have a precondition, so that everybody who wants to call the method can check, am I really satisfying this precondition? And then what do I care whether I call this method without satisfying the precondition or not? So it's much better to make it explicit as a precondition, because then you can, as a developer, you can decide, yeah, should I really call this method or not? Okay, so then, yeah, now how do we solve this issue between of calling a method and having this if y greater than x? How do we, well, maybe the first thing, how do we do this y greater than x if? Okay, between.
So if y is greater than x, it will imply that too small.
Okay. Yeah, so let's do that. Do we need any assignments, like or single static assignment variables? Probably, right? Let's keep that for now. The precondition, yeah. So now let's do this. What you just said. Now we either do an implication or okay, let's do an implication. So yeah, we can also do an if then else, right? Maybe that's better. Okay, because there's an if, right? The question, but there's no else, right? Why would we need an if then else? Why is an if not enough? Well, we don't have if in SMT, right? Okay, so let's try our if then else and see what happens, right? That's the closest we can get to the if. Maybe we don't need the else. Maybe we do. Probably we do. We will see why. Okay, then so we have y greater than x. That's our inputs, right? So we can just, that's definitely our inputs. No assignments have been made before this check, so we can check those variables, right? Okay, we want y if y is greater than x. Then we want to do something. What do we want to do? Sorry? Sorry, yeah. We said y greater than x, right? Not sure why yeah. Okay. Yeah. How can we be sure? Well, y1 equals equals what? Ooh, this gets complicated. And all the other stuff that we had in the other piece of code, right? Okay. Well, actually, this piece of code, we have already proven something about this piece of code, right? What have we proven about this piece of code? We have proven the post condition. We have proven what it does. We don't need to look at the implementation. We know what it does. So actually, we can now use the post condition as the effect of the method, because we have proven that this is always true. And actually for us right now, it's sufficient. So we can now use the contract here in this method. So instead of really executing the method again, we can say, well, we know what it does because we verified that it does exactly this. So now we're using the contract, the post condition here, and this is much simpler, right? This is some assignment. So what does this assignment do? We need some x out, right? Let's just call. Now we know we need assignments, so let's declare some variables. Well, we could even call it x out because we will not have that many assignments, right? So we have an x out and a y out. So now, yeah, we have, well, this strange assignment thing here. Maybe we don't really need this, but we need two assignments, right? So we have, let me try to get the parentheses straight. Okay, so we have, now we basically, should I indent it further? Yeah, maybe like this. So now we are in the then part of the if, right? We have the condition, then we need the value for the then. What does it mean then? And then we said, well, we actually will use this contract. So we will say x out equals the y in. So that's x out. And what is our y in? That's the y, because we didn't do any assignments yet, right? So the y in is exactly this y that we gave to the swap, right? So let's was it xy? Something like that. Okay, and then the contract has a second part that says, well, y out also equals x in. So y out would be the x, right? Okay. Okay. And yeah, then what do we do in the else case? So I mean, what happens? What's the else case? The else case is if y is not greater than x, right? So if they're equal, or if x is greater than y, what does this code do in this case? Nothing, right? Because there's no else block. I'm not sure how to write nothing. In the SNT solver, something like a constant true or something. I'm not sure if that exists. Probably not, right? Okay, good. So yeah. Well, now this assertion would, if this is not the case, then it would simply say, well, we're fine. If this is the case, it would say, well, then also this has to be the case. Great. Good. It's satisfiable, but right now we don't really. Should we look at the model? So something is not right, right? We have here 0 and -1 as inputs, and then we have the 0 and 0 as outputs. There's something not right. What's wrong? Because that is not really. So let's see. Should this thing do any work? Wait. Our y actually is not greater than the x, right? So it's fine. Yeah, it doesn't do any work. It's a bit confusing that we have this x out and xy. Sorry, x out and y out. We're actually not using them right now. So, okay. This might give us some trouble when we write the post condition, right? So let's write the post condition now to see what the post condition would look like. The post condition needs to say that x out is greater than y out, right? So, and we know, well, we need to negate this, right? Because we want to check validity. Should we just first write it normal? I'm just going to write the normal one first. So we said x needs to be greater than y, right? Because now we're checking satisfiability, so I just want to see an example where this actually works. Sorry. It's probably not a good idea to call them x out. I'm just going to call this x1 and y1 to not get it too much confused with the out, because the out had a special meaning, right? Now, what's really the out? Is that x1 and y1? Is it these? See if that works. Well, we have 4 different values here. Something is wrong, right? That's not the something is off. Okay. Are we using the right variables here? So again at the code. This y out here at the this x out here at the end of the execution. We need to see what does this variable x out actually refer to. Did we do an assignment to x? Then x out needs to be the very last assignment that we did. So we did an assignment because we reused this post condition, but we actually only did this assignment if y greater than x. If we didn't do this assignment, then what did we do? Then this x out needs to refer to the x, right? So now it gets a bit more complicated because we do have now a different control flow. There are 2 ways to execute this. One way is we satisfy this condition, we do the swap. The other way is we do not satisfy this condition, we simply jump to the end. So this means now that our, maybe we make this explicit, our x out could be different values. So let's create some kind of, well, dummy for outputs, right? I'm just going to make them explicit. We could write this in one line in the condition, but let's just make this explicit. Let's just say what these are, right? So, and we should probably, where do we need them? Well, usually we declare variables on top, but now let's put them here because we really just need them for the post condition. So here, x out, y out, right? That's what we want to do. Now we just have to say what are actually this x out and this y out, and the answer is it depends, right? So there's one case where the x out equals x1, right? If we did the assignment, it equals x1. And there's another case where the x out equals simply the x. If we didn't do any assignment, then it must be the variable on the top. And now, how do we distinguish cases? With an if then else, right? If then else usually needs some condition. Now, how do we distinguish these 2 cases? How do we know whether we actually went into this branch or not? How do you know this? Yeah, we look at the condition, right? It's this condition. And the good thing is we can evaluate this condition at any point in time because we use single static assignment. So the evaluation of this condition doesn't change. In a program, the evaluation of this condition, if you run this program twice, it changes, right? Because we do the swap. But because we did single static assignment, we can always go back to this condition and ask this condition again. So, well, yeah, the condition, we do exactly the same condition, y greater than x. If y is greater than x, then the output of x must be the assignment that we did in the swap. If, well, otherwise, it's simply the x from up here. Great. And of course, we have something like that for the y. And now let's see. So now, in all cases that we have, we're going to fix the value of x out and y out, right? Either it's x1 or it's x. So, or either it's y1 or it's y. So now this hopefully is correct. Let's look at the model. We get as input x, we get as input the -1, and then we check is -1 greater than 0? It's not. So the output should be the same as the input. So where's x out? X out is 0, like x, and y out is -1, like y. Great. We could now, of course, put some examples in. We could like give special values to the x and y and see if this method works. So yeah, let's just do this. Very simple assertions. What should we use as x? 5 or 3? Well, 5. Let's use 5 as x. And then some nice value for y. 10. Yeah, exactly. Because then we actually now have the case that y is greater than x. So that we actually do the swap. Right here, we in this model that we got randomly, we didn't do the swap, so it was not very interesting. I mean, it's good to check that it works in all cases, but let's also check the other case. Okay, so x was 5, and now x out, you should have the value 10 from the y. Great. And of course, we should preserve the y out with 5. Yeah, so there was a swap. Great. Okay, now we're probably ready to check whether it works in all cases, and we're going to do that again by negating the post condition. And it's unsat. Very good, so we are not finding anything that violates the post condition. Okay, so yeah, we had two new things. We actually learned that if we are calling a method and we already proved the contract of that method, it's hopefully sufficient to use the contract of that method. This was a slightly special case because in our case, the contract was all that matters, right? There could have been additional assignment in the methods that are used by our method calling the other method. Then this information wouldn't have been in the contract and we wouldn't be able to verify it, right? In that case, we would have had to expand the method and have a little bit more complex specification here. But because the thing that mattered was exactly the post condition of the other method that we had already verified, we could simply reuse that and yeah, simply use the contract here and say, well, we just swap the assignments and that's it. And we saw the if then else, so we saw different control flows and how actually later when we look at what are the outputs, the control flow matters. Not only when we look at the outputs, but if we would have had other assignments there, then the control flow also would have mattered, right? So this is like a prototypical way to check what are the values of the specific variables. You don't always have to introduce these constants. We just need these constants to make it a bit easier. We could have put this if then else directly here, then we wouldn't have had to define those constants, but it's a bit more readable with the constants. Also, instead of the true here, we could have simply said we only want to work with this x1 and y1, and simply said, well, we assign x1 and y1 anyways in the else branch, and we just assign them with the original values of x and y, respectively. That might have worked in this example, right? It would have been correct in this example, but in general, this leads to much more complicated translations, because then you would have to keep track of all the variables no matter where in the control flow you are, which is usually not a good idea. So the thing that you do is usually when you look at when you want to know the value of some variable, you have to kind of solve these conditions. What are the conditions of the control flow? Where I am, what might be the values there? Okay. Yeah. So here we're actually simplifying it to use the post condition because we know exactly what this swap does, and then we here we do this if then else for the x out and the y out. That's exactly the if then else's that we had, and we just gave them separate names. Okay. And this would have been the alternative encoding if we wouldn't have given it separate names. That's basically then, the same condition repeated. Okay. Now that we have already done some verification of contracts, the question is, can we do a little bit more? Could we even check equivalence of programs? Now, if we have two different maybe variants of a program, why would we ever, do we have it? Yeah. Why would we ever want to verify equivalence of the programs? I mean, the question is, why would we even end up with two equivalent programs or potentially equivalent programs?
One is more optimum than the other.
Yeah, maybe one is much faster, right? Or maybe one uses simpler operations that are less costly. Well, probably cost usually is fast, right? But yeah, so you might have different optimized ways to do something. So if you think about sorting, there are different sorting algorithms. They have different running times. They have different memory consumptions even. So you might want to prove that they're really equivalent. For sorting, it's probably enough to just have contracts, because you know what is a contract for being sorted, and then if all of them satisfy the contract, that's fine. But let's say you have some more complicated piece of code, you want to rewrite it, and then after you rewrote it, you want to make sure that it still does what it did before, and maybe that it goes faster. So that it goes faster, you can do this with experimentation, but to check really equivalence, that's not so easy with experimentation. So some of the reasons, like validate program refactorings. So we change the kind of the structure, or the structure, the implementation of the program, but we don't want to change the way that it runs. Then maybe complex compiler optimizations. So not only just for individual programs, maybe we want to check it even for the complex optimizations, and check that more efficient versions, that what you already mentioned, are still correct. And I don't know, 20 minutes ago, I said this is usually not possible, right? We can't do program equivalence because of the halting problem. And again, what we're going to do is we're going to use some very simple programs, right? We're going to use those where we don't run into the undecidability issues. In general, this thing that we're doing here is undecidable, but as we will see, for many cases, it works. So that's always the thing with SMT solvers. If we choose a theory which is powerful enough, there are cases where it's undecidable, but some cases they will work, and that's why people do it, because there's not really a better alternative to that. And we just have to live with the cases that are undecidable and maybe do something else about them. Okay. Now, how do we, what is actually the difference here? We have a different variant of our swap. You might recall that this was the swap. Here we have a different variant that instead of plus, it simply uses multiplication. And instead of minus, it simply uses division, right? So why not? So now they don't have contracts, because we don't really know what these functions do. I mean, yeah, we might remember that, this was the swap, but yeah, let's forget about this now. So those are just two functions, and we want to see whether they are equivalent. So what we need to do, we need to encode them in our single static assignments. Let's make this. Oh. No, yeah. I already have declared these variables. We'll just use them. Well, they have again this other numbering, but doesn't really matter. So let's do the single static assignments for function 1. What are we assigning here? So this x is a fresh variable, so let's use the x1 1. The reasons that they have like x11 and x21 is that they are from the different functions. So everything that is function 1 has the first a 1 and then the let's do the line number. Maybe it's better. So yeah, it's y from program 2 in line 3. Okay, so assert here the x from program 1 in line 1 will be equal to well, x plus y, but now of course this x and this y. Why do we use not x of program 1 and y of program 1? Maybe we will run into trouble later. Okay, let's see. Or maybe it's on purpose. Okay, so something like this we need. Then from program 1, we are assigning y in line 2. And this would be, well, the x, but that's the x that we already changed. So this must be the x from program 1 in line 1. And we subtract the y. And then the last thing is the x in program 1 in line 3. And this would be, well, x 1, 1 and y 1, 2. Right? Because that's the y we previously assigned in this program. So this one. Yeah. Okay. I'm guessing that. Sorry. Heck. Wait. So this one would have been the. Yeah. Okay. Well. So everything else that uses these variables. So this is again y. Yeah. Okay. I see. I probably. Yeah. Okay. Better. Yeah. Okay. Yeah. I should have been more systematic with the naming of the variables. But yeah, that's program 1. Program 2 looks similar. So let's just. I don't know. Just say. Oh. Wrong key. Come on. No. Oh, caps lock is on. Okay. Okay, so these are the assignments to the fresh variables of program 2, line 1, program 2, line 2, program 2, line 3. Great. Now let's fix the right sides here. This one must be a multiplication. This one was a division. This one was a division. And then here, this x is actually, of course, from this program, from program 2. This x is also from program 2, and this y, of course, also is from program 2. So yeah, don't get mixed up in assigning some variables from this program in the other program. This would be really a mess. Negated assertion of equal outputs. Now this is a mess because we changed all the variable names, right? So I'm just going to delete it. We will rewrite it. Yeah, let's Okay. So first, should we just kind of execute this program? We're going to say check sat and get model to see whether we find some. Well, yeah. So we have all the variables. Let's even see if it's syntactically correct. Oh, we're lucky. Okay. Seems to be syntactically correct. And we have a model. What does this model now mean? We don't have any further assertions, right? We just have implemented the program assignments. So what does it mean to have a model? The model has an x and a y. Those are the inputs. And it has some stuff with, well, x in program 1, line 3 is 0. So these are actually the outputs, right? So we now have one possible execution of these programs, one possible, well, assignment to variables in an execution of these programs. But we want to actually check that they are equivalent. So what do we need to, what does it mean for two programs to be equivalent, for two functions here to be equivalent? Now this assertion doesn't make any sense because we renamed all variables, so ignore this. What does it mean to be equivalent? This means that if we give them the same inputs, they should produce the same outputs, right? And the outputs here, well, we didn't write them explicitly, but the outputs are the x and the y values after operating on them, right? So what we need to do is we need to actually check that the outputs, now they probably have different names, that the outputs are exactly the same. We don't need to say anything about the inputs because we used exactly the same inputs, right? So we didn't double those variables. Otherwise, we would have to say those variables are equivalent, but that's we just used the same x, right? So we use the same x and y, so we're safe on that side. Now, what's the last assignment to x in program 1? This is this x13, right? So now we can put this guy back, this assertion. So x13, well, the programs are very, very similar, so that's probably x23, right? In the same x in program 2. And then the last assignment to y was this y12, right? So y12 and y22, very likely. Okay. Now, should we check again a possible run? Now, if we we saw this thing already satisfies these assertions, right? Hopefully we get a different model. No, we get exactly the same model. Okay. So now let's see if it works for all of them. Oh, there's no undo here. Okay. So, we get a model. We don't want models, right? We want ansat because we negated the equality of these two things or the equivalence of the programs. Did we do anything wrong? Let's see. So as input, we get -2 and 0. Now, we know that the one with the first program is the swap, right? So let's see if it really swapped. Because if it swapped, we know we encoded this hopefully correctly. So the output of the first one was the x13. X13 is x and y, right? And x13 should be what? Should then be the value of y, right?
Yes.
So that doesn't look good.
And I think there'll be a division by 0 in the second one.
Okay, so the second one, yeah. Let's look. Why did the first one not work? The first one, x plus y, then x minus y, and then is this even the swap? Is it exactly the swap? We add y there, then we y should then be the value of x, yeah, and then we need to remove the was this the same as swap?
Yeah. Yes.
So how come
Last statement is minus 1.
sorry?
Last statement will be x minus 1 in the program.
Yeah.
Oh, good. Yeah, so that's why we always do two exercises, one where you do it manually and then one where you automate it. Because when you automate it, it's going to take that thing and put it there and yeah. Manually, just you introduce errors. Okay, so yeah. Let's try again. Did it do a swap, at least for the first one? So x13 should be the value of y. X13 is 0. Great. Now y12 should be the value of x. X was minus 2. Y12 is minus 2. Great. So the first one swapped. What did the second one do? Did it also swap? Let's first check. Did we get all the operators right? Multiplication of x times y, and then we have divisions of the x's by the y's, and they of course have the correct replacements of the variables. Okay, so the second one is correct. What will happen in the second one? We have y equals 0, and yeah, somebody mentioned we're dividing by 0, which usually is not a good idea. Anybody remembers what division by 0 was in SMT, in the theory of arithmetic? I think it said it was undefined, so it could be any value, but it is a consistent value. So if you divide the same thing by 0 twice, you get the same strange value. So here, so x1, yeah, that's how it gives the division function. Well, that's not very helpful, right? If the x0, this must be the first parameter, is 0, and the second one is minus 1, then it gives 0, else it gives minus 1. So this means the division by 0 is probably minus 1, which, yeah, not very helpful. But this is how it messes up. So basically, this division by 0 case is not handled, and our model shows us an input where this thing messes up. It would also, of course, mess up in a program because their division by 0 is also not what you want. Yeah, the tricky bit here is that the SMT solver can actually define division by 0 in any way it wants. But because we're asking for something that violates the assertion, it will, if there is a way to define division by 0 in a way that violates it, it will find it. So that's where here with the division by 0, although this is this special case, we're on the safe side because it finds that something, if something can go wrong, it will find it, and it does here in this case. So yeah, this thing actually doesn't swap. Yeah, this means these two programs are not equivalent, and we found an input that demonstrates that they're not equivalent. So this input minus 2 and 0, we could simply feed it here. We have minus 2 times 0 is 0. Then 0 divided by 0 is, well, some exception is thrown, right? The program terminates, and then, of course, everything is lost. But yeah. So that's, yeah, these two programs are not equivalent. So the swap with the plus and minus for integers works, but with the times and the division, it doesn't work. Okay, yeah, here this would be the SMT code with slightly different variable names, but yeah. So now, yeah, quick reflection on the exercises. We said that we basically have these different parts or different chapters of the lecture. Anybody knows where we are right now? Yeah, we're basically yeah, here in this one in the middle, right in the middle. The first one was very short. It was like an overview and motivation. and what might be some applications. We always have this kind of structure where we say we look at the logic, then we look at the tool, and then we look at applications, right? So for propositional, for SAT solving, we looked at propositional logic, we looked at Limbool, and we did some applications like this role-based access and the feature model analysis. Then for SMT solving, we looked at this like what's the background of first order logic and what are these theories and these axioms and stuff. But then we switched over to the tool Z3 that hides all these tricky bits from us. And then we looked at things like code analysis. And we have these exercise blocks here, and they are always kind of two exercises. Let me check. One where we do a manual encoding to get familiar with the concepts, and then an automated encoding to actually, once we have understood how to formulate the problem, we want to generalize it. And this kind of reflects the workflow that you would have in practice. At first, you have to think, when you have a new problem that you encounter, you have to see how do you actually encode it in the formalism that you want to solve it. So it could be SAT, could be SMT, could be the other formalisms that we're going to see. And then once you understood how to do it, in many, many cases, you're not going to have to solve only one problem. In many cases, it's some generic problem that occurs over and over again, and you have to automate it. So this is why we always have those two tasks. And I think this manual encoding somehow is easier, at least based on the feedback that we get, than the automated encoding. But really, the manual encoding is always just the first step. So yeah. And for the automated encoding, there is a lot more. There are some frameworks. There's stuff like transformations, template engines that you would use in a larger project. We're not using them because they would add another layer of, let's say, technical complexity that we don't need right now. So but we are using different techniques, right? So the first thing for Limbool, you were simply creating those formulas in strings. For Java SMT, you were using an API. Was this already submitted? No. Okay, for Java SMT, you are using an API to create the formulas. Then for Alloy, the same. We're going to use an API to create the formulas. And for new SMV, we will see whether whether we get there or whether we will focus on the projects, because what we did last year, in the end we focused on the projects and we didn't have the last assignment, but we will see whether we will have it this time. But yeah, based on where we are in the lecture, probably we will not have enough time to do the last one, but we will see that. So of course we do the last chapter, but maybe not the very last automated encoding assignment. We will see. Yeah, then let's quickly do some. Let's see, how long do we have? It's 10:45. Yeah, okay, so we have 15 more minutes. Yeah, let's just do this quickly. So what projects do you think might use formal methods? We don't have to do this. Yeah. Some options. Wait, where are the options? Like you could have, well, any serious software project. So any job that you get after graduation, you will use formal methods. Or is it any safety critical software project? Or is it expensive and unique software like space travel software? Or is it only Java projects? Yeah, so automotive software, that's basically the safety critical one. Yeah. So then, of course, stuff like this here, where things really, really shouldn't go wrong. You would use formal methods for space travel. That's why also one of the earlier quotes on what are formal methods, this was from NASA, right? And there's also, I think in France, there are some very large public funded projects for railway systems, which use lots of formal methods. Yeah, the question is, any serious software project? Not really. So the thing is that formal methods, they are more on the side of the, let's say, more serious software. They take some investment. There are, of course, some formal methods that run in the background, like all these code analysis tools. Those are formal methods tools that somebody programmed, maintained, and everybody uses them, right? In your IDE, you will always use these analysis. The compiler basically has lots of form methods analysis. The optimizations, all this is form methods, but they are more in the background. So you will not actively use them like we use them here in this lecture. So the stuff where you will probably actively use them, this will be more these two here, like more safety critical. It doesn't always have to be just automotive, could be also, I don't know, if you're working on more security related stuff like this, Amazon Cloud, Amazon Web Services configurations. So there are some examples. Yeah. So some examples. So one of my colleagues, for example, he did some analysis of Amazon Web Service security configurations. We had this very, very simple thing of role-based access control, right? They basically did this by taking into account all kinds of resources and all kinds of roles. So much more complicated. They did it with I think with Citibank, and then we're checking whether Amazon Web Services wants to adopt it or not. But that's maybe also business decisions, stuff like that. Then there is right now a lot of stuff going on in analysis of machine learning, deep neural networks, for example. The thing is, it doesn't really scale yet. So they use SMT solvers, but if you think about what size the deep neural networks have right now, it's very, very difficult to analyze them. So some success stories in this using SMT solvers, they were for some like flight control and flight collision avoidance that was neural networks, but they were not so let's say large as if you want something for image classification. Then it's very difficult to fully analyze it in an SMT solver. So what people do there is they have to find all kinds of ways for abstracting the network, encoding it in SMT, trying to find solutions and trying to check, are these solutions real solutions? So you basically have an SMT solver back to back with the neural network, and you check, did this really, the solution that the SMT solver thinks is correct, is it really correct for the neural network? Because you limit the information that the SMT solver has, otherwise it just would not work in terms of performance. Then other things like scheduling of TV programs. So here, I don't know, is anybody watching German TV? There's this RTL. Do you know RTL? This TV station? Yeah. So one of my colleagues, he went to, he's now working with them, but during his PhD, he was actually developing some scheduling for the programs, because they need to like pay licenses for different movies and different series that they want to show, and the fees that you have to pay for the license also depends on at what time you show it, or what is the thing you show before, what's this thing after, how many commercials do you put in, stuff like that. This always determines the license fees. So you can imagine that some TV station, they want to optimize their programs also with respect to license fees, and of course with respect to other constraints. So yeah, they had an attempt with four methods. And then, of course, stuff like synthesis for programs. So whenever you have some, let's say, declarative specification where you say, I want my program to do a specific task, then you might use a synthesizer to automatically find a program that does exactly this task. So there is this thing which is quite popular and in the mainstream software, which actually uses program synthesis. That's flash fill in Microsoft Excel. There is this, I'm not sure what the button is called, but you can basically have some, let's say, combination of values in cells that you manually do. So let's say you have some cell with the first name, last name, and maybe title of people. Then you create a new cell where you put the title, abbreviate the first name, and then put the full last name in one cell, right? So now you want Excel to do this automatically for all the other cells. But how would Excel know this? You could go and try to write the formula yourself that says, well, take the title if it's not empty, then take the first name and cut off everything until the first letter, stuff like that, which might be very complicated. So what you can do is you can give a few examples to Excel, and then you can tell it to automatically fill the remaining cells, and that is actually based on program synthesis. So there's a big community working on that, and the guy that was leading the research team for FlashFill, he said the main challenge is that it has to work from 2 or 3 examples, because nobody will give you 10 examples of how you should format stuff. So they're actually synthesizing multiple programs, and then they rank them, like which program might work best for the user. They might all satisfy those examples, but still there must be some ranking. They should be short. They should be, yeah, I don't know, have some criteria. And then that's how they could convince basically the development team to get this into a software like Excel, which is deployed on, I don't know, millions, maybe even billions, I don't know, computers, right? Yeah, so those are some examples. One example, this is maybe a little bit of a simplification, but maybe this is something where you can see how stuff like that works, is if we have some machine learning algorithms and we want to compare the learned models. So what we're doing is we're basically taking some data sets and we're learning a model. This model has some performance attributes, maybe it's fast, maybe it's slow, but it also has some quality attributes, right? Does it sometimes misclassify things, stuff like that. So these things are important, and it gets even more interesting when the data evolves, because then your model might be outdated, right? So what might happen is the data changes over time. People change the way they use the internet, or they change the way they buy stuff. Life expectancies of people are changing, right? Job markets are changing, all kinds are changing. So this will have effect on existing data out there, and this will change some predictions to machine learning models. So what you need to do is you need to eventually maybe replace your machine learning model with an evolved version. This evolved version, there are many ways to get this. There's like transfer learning. There are some ways to update models. You could do retraining. You can do all kinds of things, right? Adaptational stuff. But now, if you have 2 candidate models, right, you have the one that is right now running in production on your system, and you have a new one that you updated. How do you know whether you can really replace one by the other, and what's the impact of it? So you can look at statistics like accuracy and stuff like that. But these statistics are usually, they work for every model. They're very generic, right? They don't tell you anything about your special case. So let's say you have 2 models. They both sometimes make mistakes, right? And let's say it's in some self-driving car, and they both make maybe equally many mistakes. So all the accuracy scores, everything is the same. So what one of them does, it sometimes misclassifies a speed sign of 50 kilometers per hour as a speed sign of 30 kilometers per hour, right? The other one, it sometimes mistakes a child in front of the car as an empty road, right? So probably, although they have the same accuracy scores, you might want to look a little bit deeper into the difference of the models, right? Because some differences, they might have a much larger impact than driving a bit too slow, right? So here is some very simple example, because this is easy to encode, and this is maybe everybody who used some machine learning tutorials might know this example. That's the iris data set. It has, I think, 4 features. The sepals and petals, and their length and width, basically. For both of them, the length and width in, I don't know, maybe centimeters. And there are 3 classes. I mean, to me, these all look the same, but these are actually the 3 flowers of different classes. So these are all iris flowers. This is the versicolor, the setosa, and the virginica. And yeah, there's then some model where we basically have a huge data set, and we can learn a classifier to then check which one of these iris flowers do we actually have. So yeah, nothing probably life-threatening, well, unless one of them is really poisonous, I don't know. But yeah, just an example. And one possible machine learning model that is, yeah, very simple, but still quite popular because of the interpretability, that's decision trees. So a decision tree has a decision in every node, except for the leaf nodes. And here, this first one, we see it decides based on the width of the petal. And if this is less than 0.8 centimeters, then it goes to yeah, this branch and says, well, it's of the class Setosa. If this is not less or equal to 0.8, then it goes to this node here, and then also checks the width of the petals, and then it might decide based on the width to either predict it as versicolor or as this Virginica. So this is a very, very simple one, right? This has some misses. We can actually see the misses. So this is the data sets. They're always split 50-50 for each class. And here you can see the classification. So it's a perfect classifier for this first class. It doesn't misclassify any of the two other classes in this leaf, right? And then here you see that it is correct on these 49 out of the 50 when it says versicolor, but it misclassifies those 5 out of the other class. So there are some misclassifications here, and then of course, yeah, equal problems there. Okay, so we can also have longer, like taller ones. The depth of the tree can be larger. Now we see that some leaves, they are just like for the like remaining classes, stuff like that. But now, how would we compare those two? How would we compare this one and this one? How would we see what's the difference? Is there any, let's say, special case where they disagree? And the way we can do this is we can encode them into SMT. It's like our programs where we have an input and we have an output, right? We can say, well, a classifier, now it's a decision tree, but could be other classifiers as well, right? A classifier is something that takes as input assignments to the features, and it gives us output a class prediction. It tells us which class did the classifier predict. And then, yeah, how do you now encode a decision tree? Well, that's actually not so difficult. What you could do is you could look at each leaf, because the leaf says which class it is. And then you can say, well, how can I get to this leaf? And there's only one way to get there from the root, because you always start at the root, so you can basically go backwards. And this gives you this one condition for this class, another condition for this class, and another condition for that class. They can overlap, but here actually the classes of the leaves, they were unique, and we see here, well, that's less or equal petal width 1.75. So these conditions are the ones that we need to add up. So if we are here like greater than 2.45, and here we are less than 1.75 in this feature, then we end up in this node. Great. So we can basically encode this classifier, and we just simply say, well, ending up in the node means we are assigning the version 1 class prediction to 1, 2, or 3. These are just the indices of the classes of the prediction. And then this one, well, yeah, this sometimes has a little bit longer path, so we have to compare more features. Yeah, like 1, 2, 3 feature comparisons, and then we know whether we are left or right. And then we can assign, yeah, the class values again. And now we have kind of encoded the classifiers as programs. And then we can analyze the differences. We now want to see where do the two classifiers disagree. So these are potentially interesting cases for us. And the features, they simply share, right? The length of the petal and the width of the petal, and maybe do they only look at those two features?
So
Two. So each, so actually these ones, they predict the same class. They have the same class label. It's not really shown here nicely. The reason is the one with the highest index in the array, that's the class it predicts. So here it would predict class, well, the last one is true, I guess. Yeah. And this one, sorry, this one would be 1. So that's this prediction here, I guess. And this one, the highest number is at index 0, so this would predict the class 0. But that's specific to decision trees, right? So this is always the possible values of these classes. They are based on the classifier or the data set that we put in, right? Okay, and then we can check, for example, do they always agree? And if they not agree, then what we get is an assignment to the features, because those are the only variables that are left to decide, right? It will give us an assignment to these variables that makes the classifiers disagree. So what we get is we get some description in terms of the features of this iris flower, where the two classifiers would, well, one must be wrong, right? If they disagree, one of them must be wrong, or both, right? Okay, yeah, so that's one way we could use them, for example, for analyzing machine learning models. Yeah, that's the summary page. So basically, we can encode all kinds of different programs, right? From machine learning to program analysis to configurations of PCs. There are many different ways. So we saw like this puzzle with the houses. We could use booleans, we can use integers, we can use data types. They all have the pros and cons. Some are better for performance, others are not. And yeah, there are many like practical applications like program analysis. Okay, yeah, that's it for today. And this means on Friday we are continuing with the next chapter, the first order relational logic. Okay, so see you on Friday.